Hey, well, welcome back. Last time we talked about magnets and magnetic fields and electromagnets and how we can set up those magnetic fields with symmetry. So today we're going to talk about magnetic forces. So let me just, before we get started and get into the details, let me point out a nice kind of symmetry around magnetism. You know, physicists, we love symmetry. Nature appears to be deeply symmetric. And here's a good example of it, right? So on the left-hand side, we know things about the magnetic field that we talked about last time. That is that the charge has to be in motion, right? So if you want to make a magnetic field, that comes from not just charges, but charges that are in motion, right? And then those magnetic field lines actually come in loops, right? They loop around the charges. And depending on how those charges are situated, those loops may get distorted. They don't have to be perfect circles or anything, but they will loop around on each other. So that is about on the production side. And what I've done over here on the right-hand side is I've shown you about how the forces work. So just like you need a charge in motion to produce a magnetic field, we have this kind of strange situation where magnetic forces, are only felt by moving charges, right? So if you stick a stationary charge inside of someone else's magnetic field, it will not actually experience a magnetic force, right? So just like charges in motion are needed to produce the field, charges in motion are needed to feel the field, to experience that magnetic force. And what kind of force do they experience? Well, they have forces that are at right angles to their motion. And so if you think about what that means, that will be something that causes you to turn. And if you continue to turn, of course, you will loop around. So for instance, we talked about this last time. These charged particles come in from outer space. They hit the magnetic field lines around the Earth, and they start to spiral around. So why do they spiral? It's because the charge in motion is coming in on one direction, and then it experiences a magnetic force that causes it to turn. And as it turns, it continues to turn, and that will cause it to loop like this. And so this is a very classic thing where you get a lot of circular motion for magnetic forces. For instance, in a lab, if you have a uniform magnetic field and you shoot a charged particle in, you'll frequently get a spiral like this, right? The spiral in both cases comes from a combination of a perpendicular component of the velocity and a parallel component, right? The parallel component is not crossing any field lines and doesn't experience any force. And it's actually only the component of the velocity vector that is crossing the magnetic field lines that's considered to be moving relative to the magnetic field that causes it to have a magnetic force. All right, before we can actually get into how the forces work, we need to talk about vectors in 3D. We may have talked about this before. Anytime physicists go into 3 dimensions, we have a convention for arrows, right? You can draw 3D pictures, but they're kind of confusing because paper and screens are, of course, 2-dimensional. So the way we draw vectors to indicate the third direction, right, that would be into or out of the sheet of paper or into and out of the screen, is a circle with a dot represents the tip of the arrowhead coming straight towards your eyes, right? So that's an arrow pointed up out of the paper. And a circle with an X, or just the X itself, is like the tail feathers of an arrow as the arrow dives into the paper, right? So this is a convention widely used by physicists mostly, but mathematicians as well, to indicate the third direction, like the Z direction of vectors, right? If it's in the plane of the paper, we just use up and down and left and right arrows like we've been doing. All right, so because magnetism is 3D, we're going to need to use those, okay? So here's an example of circular motion that comes from a magnetic field. What you see on the left-hand side here is there's a magnetic field that has been set up by objects that we don't see, right? So we can figure it out in a second, but let's see, we've got a blue field of blue X's. So that means the magnetic field represented by these blue arrows is pointed into the page, right? So that could be set up in a number of different ways. The easiest one would be to hold a north pole just above the page, right? If we had a big fat magnet and we held it just above the screen here, then the magnetic field lines would be coming out of the north pole of the magnet, and so they would push through and into the paper. That would be one way of doing it. Like for instance over here, right? You got a north pole, magnetic field lines are coming out, so this sheet of paper here would be like in the plane in between these north and south poles. But anyway, let's stay over here for a second. All right, what do we got? We've got a negative charge that has a velocity to the right at point P, And so I told you that the forces are going to be at right angles. And so that means it's going to be inwardly directed to the circle, which makes sense, right? That's what's causing it to undergo circular motion. Magnetic forces are centripetal by their very nature, right? Since they're going to be at right angles to the velocity, they're always going to cause you to change the direction of the velocity vector, right? And everything is constant, you'll get a nice circle like this. So a little bit while later, it'll be at point Q. Now the velocity is in this direction. The magnetic field lines are still these x's, and so what's at right angles to both the green arrow and the blue arrows would be this red arrow. So how do we determine that? We're going to use a version of the right-hand rule. Now there's lots of different ways to do this. The most common one, I guess, would be to take the thumb of your right hand and stick it in the direction that the positive charge is flowing, right? Everything is in terms of positive charges. So unfortunately, in this picture, we have a negative charge that is going to the right. So that means you're going to need to point your thumb to the left, right? A negative charge going to the right is the same thing as a positive charge going to the left. So point your thumb in the direction of the motion of positive charges. Then point your fingers, all four fingers together, in the direction of the magnetic field. So that will be straight into the page. And then close your fingers into the palm of your hand, and that will point in the direction of the force, right? That's how you know the force is down and not up, because your fingers, once you have your thumb to the, either your right hand's thumb to the left and your right hand's fingers pointed straight at the screen, when you close them, they will close in the down direction, right? You're only using the right hand rule really to pick out one of two different directions, right? There's only two directions that are at right angles to both the velocity and the magnetic field, and that is, the velocity vector is left to right, the magnetic field is in and out, so that means you're just picking out between up and down. So that helps to clarify it, I think. The point of the right-hand rule is not to pick out any arrow, but just to pick out one of the two. Over here we have two examples, one with a negative charge and a positive charge. So let's do the positive charge. If you shoot a positive charge into the page, that means you're going to stick your thumb straight in at the screen, and then you need to orient your fingers to the right, because the magnetic field lines are going to the right. And then when you close your hand, you will find that your fingers close in the downward direction, right? And so the positive charges will bend downwards. Negative charges, on the other hand, right, will go the opposite way. They always do the opposite thing. And that's because you need to point your thumb out of the page. Your fingers would still be going to the right, but then when you close them, you'll be closing them in the upward direction. And this, in fact, is how they sort charged particles very easily. In the early part of the 20th century, late 1800s, when they were trying to figure out whether things were positive or negatively charged, this is what they did, right? They shoot them into a magnetic field, and the neutral particles would go straight through, and the positive ones would curve one way, and the negative ones would go the other way. Here's the formula to go with the right-hand rule, right? So this is how you find the magnitude of the force, and you're going to use the right-hand rule to pick out the direction. So obviously force and magnetic field are vectors. So is a velocity, right? And so you have three vectors. This is actually a cross product here. And let's see, what do we have here? The B is the magnetic field strength. B is traditionally used for magnetism. Q is the charge that's traveling through the magnetic field, and V is the magnitude of its velocity. And then the sine theta is going to pick out the component of the V that is perpendicular to the B vector, right? So this theta is defined to be the angle between V and B. This is exactly like the torque equation, right? We're replacing QV with R, replacing B with F, and then sine theta to pick out the perpendicular component. And that's because mathematically torque and magnetic forces are both cross products. If you have a whole bunch of current, a whole bunch of charges moving in a straight line, well, we call that a current, I, in amps. And the velocity is already in there in that we have charges per second. What we're missing is the meters in the speed, and that will be the length of the wire that is actually in the magnetic field, right? You wouldn't use the entire length of the wire, just the portion of it that is inside of the magnetic field. And so that is the current in amps times the length in meters of the wire that is carrying that current inside the magnetic field B, and then sine theta once again to pick up the perpendicular. So these are two different ways of really writing the same equation if you think about the units. Last time, I don't know that we talked about the units of magnetic field. The metric SI units are Teslas, named after Nikola Tesla, who did a lot with magnetism back in the day. So as long as you have your magnetic field in Teslas, and then your current in amps, or your charge in coulombs, your velocity in meters per second, your length in meters, you'll get a force in newtons. Okay. All right, let's go through a couple of different examples. The right-hand rule is confusing. So let's say we've got a battery here that is creating a current. Current is defined to be the flow of positive charges. So they come out of this high voltage side, they flow around this wire, they go into the page here, through and then back, right, and to complete the circuit. So we're just concerned about the portion here that's in the magnetic field. So I'm going to stick my thumb of my right hand in straight at the screen, and then I've got to stick my fingers horizontally to the right, and now I close them into the palm of my hand, and I find the force is downward, right? So that means that this wire would actually experience a downward force inside of the magnetic field, right? How strong that force is depends on how strong the magnetic field is and how many amps are running through the wire. If the amperage is low and the magnetic fields are low, you're really not going to get much of a magnetic force at all, right? So that's why in most circuits with low current, you don't really have to worry about the wires getting moved around by magnetic fields. But if you've got very thin wires that are easy to move and strong magnetic fields or strong currents, then you do have to worry about it. I had another thing to say that's escaping me right now. All right. So if you reverse the direction of the current, say the positive and negatives have been reversed here, so we've reversed the flow of current, you will get the opposite effect, of course. And then here is another abstraction. Let's say we've got magnetic field lines going to the right, current that is going through the page, and there is a theta now, so we're not necessarily going at right angles. So when you use the right-hand rule, you can just simplify it and make the angle 90 degrees, right? Because you're still just picking out one of two directions. So in this case, you've got your thumb pointed into the page, the magnetic field line's going to the right, and so you're going to recoup this picture over here, and you're going to get a force that's downward. The role of this theta is it won't be maximum, right? Over here, you've got a theta that looks like it's 90 degrees or very close to 90 degrees, so that'll be maximum force. This theta looks like maybe it's a little bit less, and so the force will be less. If the theta were 0, right, and the current were going in the direction of the magnetic field lines, then you wouldn't actually have any charges crossing magnetic field lines, and you wouldn't expect to get a force. And of course, the sign of 0 will give you that. Okay, here's a more complicated example. We've got a current running down the middle of the screen, and we've got 4 charges in motion. So what we have to do is we have to figure out why would there be any magnetic force at all, right? And the reason is because this current, we know, is going to set up magnetic fields around it, that loop around it. So we've got to use our right-hand rule from the last time. We've got to point our thumb to the right, and then that our fingers will curl around and tell us that, oh, magnetic field lines are coming out of the page up here, curve around through space in front of our nose, and then go dive back into the page here, and then curve behind it and come around like that, right? So that's how the magnetic field lines are looping around. So in terms of direction, all we really need to know from that is that the magnetic field lines above the wire in this area over here are all coming out of the page. They'd be represented by dots. And the magnetic field lines down here below the wire in the page would be all going into the page, so they'd be represented by X's. And that's all we need to know in order to apply the right-hand rule for these 4 individual cases to figure out the force. So let's do this one. It's a positive charge moving to the right. So I stick my thumb to the right. We just decided the magnetic field lines are coming out of the page. So when I close my fingers, they're pointed down. So this guy's going to experience a force in the downward direction. Okay, here I have a negative charge that's moving up. So I'm going to point my thumb in the down direction, right? The down direction because it's the flow of positive charges. And then my fingers, once again, need to be pointing out of the page because I'm above the wire and all the magnetic field lines are coming out of the page. And then when I close my fingers, they will be pointed to the left. And so this negative charge will experience a force that's to the left. All right, now let's go down here and do these 2 cases. Let's start with the positive charge. So positive charge is going up, stick my thumb in the up direction. The field lines here are coming, what do we decide? Into the page, right? Into the page. So thumb up. My fingers are pointed into the page, and when I close my fingertips, they'll be pointed to the left. So this guy will experience a magnetic force that deflects it to the left. All right, and this is a negative charge moving to the left. So I'm going to put my thumb to the right, my fingers, once again, into the page, and then when I close my fingers, they will be pointed in the upward direction. So this guy will be deflected upwards. Okay. This is a classic physics problem where you get two wires nearby each other. So each wire is going to be producing its own magnetic field, right? So I1 will be creating a magnetic field out here to the right, and I2 contains charges in motion inside someone else's magnetic field, so therefore it will experience a magnetic force, right? And at the same time, I2, I mean, that's the picture over here. So I1, here's the picture of all the magnetic field lines. You can see they're going into the page over here where I2 is. At the same time, I2 is setting up its own magnetic field lines around it, and I1 is moving through there. And so I1 will experience a magnetic force due to I2. And that should actually be reassure you. Look at these two arrows, right? Do they remind you of something that we learned, in the first week of physics class? This is an action-reaction pair, right? I1 is exerting a magnetic force on I2. That magnetic force turns out to be to the left with the right-hand rule. So you don't need to know anything about magnetism. You just have to know that how forces work. Newton's third law says if I1 is pulling I2 to the left, then I2 is pulling on I1 to the right. Right? And so if you have currents that are going in the same direction, they're pointing in the same direction, they will exert attractive forces on each other. You just got to go through the steps of the right-hand rule. If they are going in opposite directions, it shouldn't surprise you. You get the opposite, and they'll get repelling forces. Okay, so that's how forces and magnetic fields work, right? The right-hand rule, and then these formulas back here to actually figure out the magnitudes of the forces. Let me just show you a couple of everyday examples that rely on magnetic forces, right? So a speaker and a microphone are actually the same device. They both have jobs of, in a speaker's case, you're taking electrical current and you're moving air to create an air pressure wave, which is a sound wave. And a microphone is just doing the opposite. It's taking the energy in from the sound wave, which then moves this cone that's inside the microphone, and then that moves the magnet inside of here, and that creates a magnetic force on the charges in the wire and creates a current. So basically, what happens is inside of all of these electronic devices, so many electronic devices use this trick. I was talking to you about in the last lecture about how your automatic car doors work. They do this trick as well. There'll be a permanent magnet inside and a coil of wire, which is the electromagnet, right? So the magnet by itself creates a magnetic field, which then has no effect on this if there are no charges in motion, right? But by sending a current through here, you then create a magnetic force on there that's at right angles to it. And that magnetic force will then cause this electromagnet to move to the left or move to the right, which then has this cone attached to it, which is moving the cone left or right. And by reversing the direction of the current in here, you can reverse the direction of the force. And by controlling the frequency of the current through here, you can control the frequency that this goes back and forth, and that is literally the frequency of the sound that's created, right? So if you want to, make a middle A 440 hertz, you send an AC current through this coil of wire at 440 hertz, and it will dance back and forth 440 times because of the magnetic field, right? You orient it so that the magnetic field is at right angles. The magnetic force is at right angles, will cause this to move back and forth, and then the frequency will control how often it goes back and forth. The other one, even more common, is every single electric motor, right? Any motor that is driven by electricity is working on this principle. It also has a coil of wire in there and a permanent magnet, right? So the permanent magnet, just like in the last example, sets up a magnetic field that may or may not exert forces on a wire in there, right? This is just one loop here, but a real-world magnet would obviously have many wrappings around there to increase the effect. If there's no current going through here, then the permanent magnet has no effect on it, right? But as soon as you send a current through there, you plug in your electric motor and turn it on, you send current through this coil of wire, now all of a sudden you have moving charges inside a magnetic field, and when they're moving up on this side of the coil, they'll be moving down on this side of the coil, which will cause forces in opposite directions. You can see these red arrows, right? This is a force into the page, and this is a force out of the page. Well, what happens if you have something that is free to spin, and you push down on one side and up on the other, is you'll get it to rotate around. You can see it's labeled right here, this axis of rotation. So every electric motor in the world relies on this principle of having a permanent magnet in there. If you don't believe me, take a magnet from your refrigerator and go test it on any motor in your house, and you'll find that refrigerator magnet is strongly attracted to the motor because it has a permanent magnet in there. Every motor has a permanent magnet in there and a coil of wire that is free to turn. It is possible to have two coils of wire in there, and it is also possible um, that the magnet turns and the coil of wire is stationary, right? Those are all permutations that would work too, but this is the most common kind. I'll show you a picture in a second. This is a top view, right, where the axis is coming towards you, and you can see those opposite forces cause you to turn. And this is why when you buy electric motors, they always talk about torque instead of force, and they talk about the RPMs of the motor, right? Right. Even in your car, even though your car is a combustion engine, uh, it is also driven by rotation. So here's a more kind of realistic view of what one looks like on the inside. If you dissect it, it'll have some kind of permanent magnet out here, north and south pole, to set up the fields. And then you have like a cylinder usually that's, a wire goes around here like 100 times or 50 times or 1,000 times, depending on how the motor is designed. And then that whole thing that rotates, that rotating electromagnet is called an armature. There's just so many different synonyms for electromagnets, but that seems to be the one I see most commonly with electric motors. One thing that's kind of tricky is if you're running this off of batteries, you need the current to switch halfway through the cycle, right? Because the north pole, when you're on this side, when the wire's on this side, you get a force in one direction, and then when you go over here, the force would be in the opposite direction because you're going through the field in the opposite direction. You're crossing the field lines the opposite way, and so you would get a motor that kind of goes 180 degrees and then goes back, right? You wouldn't get this continuous rotation. So the trick is, and this is something Nikola Tesla invented, I think, is you want to switch the direction of the current and time it perfectly so that when the wire is on this side, the current is going one way, and then by the time it rotates over here 180 degrees, you want to switch the direction of the current. And it's the timing of the switching of the current and the rotation of the armature or the electromagnet inside of here that's so key. And there's several different ways to do it, but the most common kind is if you dissect an everyday electric motor, you'll find that the electrical connection here is loose and there's just these brushes that are touching here, making an electrical connection by contact, but it's not soldered on or glued on or anything like that. And so as it rotates, this nub of metal here that's in contact with the wire is connected to the brushes on this side through this nub of wire. When it rotates 180 degrees, these brushes are stationary. You'll see that this one is in contact over here, which is the positive side, and that one's now in contact over here, which is the negative side. And so just the rotation itself will accomplish the reversal of the direction of current, right? So oftentimes when you plug a motor into an alternating current outlet in your house, it will actually get converted to DC before it goes to the motor. There are also AC motors, right, that just take the AC in directly. The brush that's called the commutator, these connection points, right? So there's all kinds of technology going on inside of here. But that's the basic idea behind an electric motor. So electric motors rely on magnetic forces, right? You're taking electrical power from a battery or from a generator that's bringing the electrical power into your house. That it creates a current in here, and then that current experiences a magnetic force, and then you get mechanical energy out of there, right? So you've got electrical energy that then experiences a magnetic force, which does work on this axis, which then turns whatever you've got out here, the fan or whatever is being turned by this electrical motor. And so at the heart of every electric motor, there is rotation driven by magnetic forces. Okay, good place to stop for today.